In this video, we're going to take a look at the concept known as differentiability. Now, we've come across a related concept, and that concept was continuity. And a big part of continuity, like from an intuitive standpoint, was like, what properties does the graph of a function have? So we know for a function to be continuous at a point, it cannot have any removable discontinuities, so it can't have any holes. It can't have any jump discontinuities, and it can't have any infinite discontinuities or vertical asymptotes, right? So we have this kind of visual way of identifying when a function is continuous at a point and when it's not. Well, it turns out we'll develop something similar for this new concept known as differentiability. So let's kind of set the stage for what this is all about. Now, going back to the very first limit definition that we came up with, and let me remind you of that one. So that's when we were finding the slope of the tangent line at a specific point, and we started with this limit, and this was our difference quotient, right? So a was a fixed number, and we had our function f of x, and we came up with this process for finding the slope of the tangent line at that specific point. And then we modified this slightly and came up with an alternative definition, but that was the limit that involved h going to 0. But it was still at a specific point, so we had expressions like this, f of a plus h minus f of a all over h. So again, both of these represent the slope of the tangent line at a specific point. But then we realized if we had to do this process for different values of a, then it becomes extremely tedious. And then that led us to the idea of, instead of plugging in our specific number at the start, why don't we keep our variable x there, and then after going through our limit process, evaluate the result, right? So instead of evaluating at the start, we essentially evaluate it at the end. And that limit looks like this. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is what we defined as the derivative, and we introduced that notation, right? But the one thing, if you remember, every time we wrote down one of these limits, there was the little disclaimer or caveat saying that, okay, whatever we're going to call this thing, whether it's just a number that represents the slope of a tangent line, or this function that we're going to call the derivative, we always ended our definition with the phrase, provided the limit exists, right? So provided the limit exists. Because there's no sense in defining a quantity if the limit that we're using to define that quantity doesn't exist, right? But thus far, every example we've done, right? The limit existed, right? We were able to either get numbers out of the process after doing a bit of algebra in some cases, or we were able to get a function, again, which is what we call the derivative. So the question that remains to be answered is this: in what instance will this limit not exist, right? So that kind of leads to this question: when will, and I'll just say, like, these limits not exist, right? And we could take a very theoretical approach, but what we're going to do, similar to what we did for continuity in terms of identifying the types of discontinuity, now we're going to take this graphical approach and say, well, what will it look like on the graph of a function if the limit does not exist, right? So the short answer to this question, when will these limits not exist? And the answer would be whenever a tangent line, right? Because that's what these all, that was our starting problem, to find the slope of the tangent line. So whenever a tangent line fails to exist, right? Fails to exist. So in other words, if we don't have a tangent line, then for sure we can't talk about its slope, right? And there's one little disclaimer, there's a special case that we will talk about when there is a tangent line, but something else happens to its slope, all right? So let's take a look to see when it is not possible to draw a tangent line. And what I will do, I'm going to sketch 3 functions. Right, so let's say we have that function. And in fact, let's even put a dot right there. Right, and then here's another one. Let's say that one's shaded in, and then that one's open. Say something like that. And then let's take a look at maybe something like this, going that way, and then that way. And at each of these points, I'm just going to label the x value as a. All right. So for these 3 types of functions, if I were to say to you, draw the tangent line at x equals a, that would be impossible to do, right? Impossible, or it would be like not a well-defined set of instructions. Because for instance here, since the point, right, is actually not on the graph of the function, then there's no way for me to draw the tangent line to this function at this point, right? Because again, if I try to draw it here, well, there is no point for the line to go through. All right, so that in itself is a problem. And then if I tried to just have it going through this point, then the question is, what is its slope? Does it look like this? Does it look like this? Does it look like that or that? So that's the thing. If our function, right, has a removable discontinuity, you could argue it both ways. Either you have no tangent line at all, or you have too many, which in this case would be ambiguous, because then not almost, but everyone in the world would be able to draw a different tangent line with a different slope. So it wouldn't be well defined, right? So that's one problem. And a similar problem happens here if you have a jump discontinuity. Again, I couldn't have it passing through this point because this is actually not a point on the graph. That's why it's an open circle. Maybe I need to make that open circle a little more distinct. Not so yeah, there's nothing there for me to have the tangent line pass through. And if you try to put it at this point, because it's kind of at the end, you run into the same issue. Does it, let me use red again. Does it look like this, or like this, or like this, right? So you run into the same issue, either not having a point at all, or in this case, because it's kind of at the end of one of the pieces, its slope is not well defined. And then if it's not clear at a tangent, at a vertical asymptote, then I don't know what is. In other words, where would I even put it? right? Where would I put the tangent line at this point? Because there is no point on this uh, function at x equals a. There's not even a hole, right? And again, that's what happens at your infinite discontinuities. And even if you said, well, we looked at cases where like only one of the one-sided limits was infinite. So in other words, let's take this part off here. And let's say this is one of those weird piecewise functions where one-sided, let's say this one-sided limit is infinite, but yet it has a finite limit, let's say from here like this. And even let's shade it in, right? Let's try to be clever. But then we run into the same issue as we have in the previous cases. It's like, what is the direction? What is the slope of this line? Is it that way? Is it that way? Is it that way? Right? So one answer to this question, when will these limits not exist? They will never exist at a point at which the function has any kind of discontinuity. All right, so let's write this down. So I'll say either in fact, let's just say f prime of a, so which is what we're using to represent the slope of the tangent line at x equals a. So this is a notation to say at x equals a, the slope of the tangent line can be represented like this. And what we're saying now with this kind of graphical analysis is that f prime of a will not exist, right, if our original function, if f of x is not continuous. And it doesn't matter what type of discontinuity. If f of x is not continuous at x equals a, right? So again, what this means is if f of x is discontinuous, right, then it means f of x is not differentiable. So the word differentiable here is used to describe whenever one of these limits would exist. So if the function is not continuous, then it's not going to be differentiable at that point, right? Okay. So those are a couple of things to look for, and these are things that we've already learned how to identify. Well, it turns out there are other problems with differentiability. Problems in the sense that we could have a function that doesn't have a hole, a jump, or a vertical asymptote, and we still wouldn't be able to draw a tangent line, right? Well, what do those look like? So the first one, I'll draw a couple graphs like this. Yeah, I'll just draw two. So for instance, let's say you have one of those piecewise linear functions. It's like your absolute value that comes to a sharp corner like this, right? So it's those v-type functions, assuming they open up like this. So you have a function like this, and then you have some functions like x to the 2/3 or something like that, that might look something like this, where they're not like piecewise linear, but then they come to a sharp corner right here, right? So you have these functions that look like this. And the thing is, these functions are continuous because they don't have any holes, they don't have any jumps, and they don't have any vertical asymptotes. But what they have these sharp corners. So these are sometimes called nodes. These are sometimes called cusps. But the problem is, again, if I asked 5 people to draw a tangent line at this point, it's quite likely that I could get 5 different answers. Why? Because look, one person could draw it like this. So I do have a point for it to pass through, but because the graph seems to like almost change. Now the word direction here isn't well defined, but it changes so rapidly that you hit the sharp corner, and the question is, does the tangent line look like this? Does it look like this? Does it look like this? Does it look like that? Right? So we still run into that same issue about slopes, right? Not being well defined. And the same thing happens on, a cusp like this, or like that, or like that, or like that. Again, they all pass through that specific point. Again, let's call it x equals a. But the problem now is still one in which we can't draw a well-defined tangent line, right? So for this one, we say if f of x has a, again, you can call it like a sharp turn or a sharp corner. So it has a sharp corner at x equals a, then again, f prime of a will not exist. We can't find a well-defined slope, right? So then f prime of a does not exist. All right? So we can see discontinuities, bad. Sharp corners, bad. There's one more bad thing, and it shows up on functions like x to the 1/3 power, like cube roots, fifth roots, and so those kinds of graphs, they actually have a well-defined tangent, but look at what the tangent line does. So the type of function that I'm describing is a function that looks like this, right? Where it looks like that. And let's say this is at x equals a. The problem at x equals a is I can draw a tangent line. But look at what that tangent line would have to be. It would have to be a vertical line. So it would have to go straight up and down. Right? And what do we know about vertical lines? Vertical lines, right? So vertical lines have no slope. Or what you could say is their slope is infinite, because it's all rise and no run, meaning the run, not no run, but the run is 0. So you'd have some number in the numerator, and then you'd be dividing by 0. So you could say no slope or an infinite slope, but what it is it's an undefined slope. Right? And because the slope is undefined, then again you would have a problem trying to use your limit definition, right? So these 3 properties that are best illustrated from a graphical standpoint, they all are indicators that your function is not continuous at a specific point. So if the function is not continuous, or if it has a sharp corner, or if it has a vertical tangent line, then the derivative will not exist, right? So again, let's just kind of summarize that. So any kind of discontinuity, any kind of sharp corner, and any kind of vertical tangent line, all these imply f prime of a does not exist. All right? But so basically, for f prime of a to exist, you have to have a nice continuous function that doesn't have any sharp corners and functions that don't have any vertical tangent lines, right? So when f prime of a exists, we say the original function, so f of x, is differentiable. All right, so that's now the property, or the word that we use to describe the property that at any point on this graph, right, then we can construct a tangent line. And if that's the case, then we would say the function is differentiable at all points. Similar to how we can say, like, certain types of functions are continuous at all points. Now we have something similar, but differentiability requires a little bit more. We can't allow sharp corners, and we can't allow vertical tangent lines. All right? But there is one property that's really useful, is that, so we've seen where continuity is not enough, right? Because we can have a function that's continuous, but if it has a sharp corner, then it's not going to be differentiable at that particular point. The converse, however, is that if the function is known to be differentiable, then it has to be continuous, right? So we will end with this theorem. And the theorem says, if f of x is differentiable, right, at x equals a, then f of x has to be continuous at x equals a, right? And let's actually give a fairly simple proof of this, and it just has it has to do with using the limit definition. Now, remember what we know about continuity. Let me just kind of remind you what continuity says. Continuity says that the limit, the two-sided limit, as x approaches a of my function, is the same as the function value. So what we're going to do is assume that the function is differentiable and then conclude that this has to be true. All right, so let's take a look at this proof. All right, so because we're told that f is differentiable, so because f of x is differentiable at x equals a, we know that this limit exists. I'm going to go back to the very first one for this. So we know that this limit exists. All right. So now what I'm going to do is to take, I'm going to look at, so now let's just look at the limit of f of x, right? So consider the limit as x approaches a of f of x. So what I want to do is to show that this is going to be equal to f of a. And at some point we have to use this we have to use this limit, right? So so in fact, actually, let me modify this slightly. So what I'm going to show is that this limit is equal to 0, right? So let's consider this expression, and what I'm going to do is multiply the top and the bottom by x minus a, right? So this will be equal to the limit as x approaches a. So multiply the top and the bottom by x minus a. So it will look like this. F of x minus f of a. Then I'll have times x minus a there. And then in the bottom, x minus a, right? So I'm taking this expression and I'm multiplying the top and the bottom by x minus a. Now, because we know that the limit of the difference quotient, which is this part, because I know that that exists, then I can use my limit properties for the product and say the limit of this entire expression is equal to the limit of what I have in red times what I have, the limit of what I have in blue, right? So use our limit properties, and this is the limit as x approaches a, f of x minus f of a over that quantity, and then times the limit as x approaches a of this quantity. But this we know is f prime of a, and we know it exists, so it's some number, and we use this notation to denote it. And then this expression here is equal to 0 because I can evaluate it, so I will end up having f prime of a times, when I evaluate it, a minus a, so that's 0. So look at what we started. We've shown that the limit of this difference, right, under the assumption that the limit of our difference quotient exists, the limit of this is equal to 0. So let's kind of summarize those three lines. So therefore, the limit as x approaches a of the quantity f of x minus f of a, that's equal to 0. But again, let's use our limit properties. We know that if we have the limit of a difference, I can take the limit of the first part and then minus the limit of the second part. So this is the limit as x approaches a of f of x minus the limit as x approaches a of f of a. But f of a is a constant, right? So whenever you take the limit of a constant, notice that this doesn't have x in there at all, right? And we're saying that this is equal to 0. So because f of a is a constant, the limit of that constant is the same constant, which is f of a. So let me write that more clearly. So then the next step is this, the limit as x approaches a of f of x, right? That's the first term, minus this constant is equal to 0. Well, if I add f of a to both sides, look at what I end up with. I have that the limit as x approaches a of f of x is equal to f of a. And this is our definition of continuity. So therefore, f of x is continuous at x equals a, right? So the conclusion is, if you know that the function is differentiable at a particular point, in other words, it doesn't have any discontinuities, it doesn't have any vertical asymptotes, any kind of sharp corners or vertical tangent lines, then it must also be continuous there, right? So differentiability implies continuity, but continuity does not necessarily imply differentiability, right? So a few very important concepts here, and I think knowing when you can look at a graph and tell if it's differentiable or not is really important, and then knowing that if the function is differentiable, then it has to be continuous, which is the essence of this final theorem, are the key concepts that you want to take away from this video. See you in the next one.